So the title of the course, if I remember correctly, is all right, self-similarity and the Einstein vacuum equations. All right, so very briefly, what do these things mean? All right, so let me start. So the Einstein vacuum equations, these are the equations that govern general relativity. I'll say a lot more about in a second, but just for now, you should think these are the equations that for this course, they will be the equations that the Ricci curvature, the metric is zero, or some Lorentzian manifold, Lorentzian manifold MG. All right, this is the setting of general relativity in the absence of matter and with zero cosmological constant, which will be the focus, at least for the vast majority of the course. What does self-similarity mean? This is well, we'll get into this more precisely later, but now let me just say something very informal. This refers to a space-time. So space-time here referring to one of these Lorentzian manifolds solving the vacuum equations, which is invariant, put that in quotes, under rescaling time and space. Under time and space rescaling. All right, the basic idea is sort of that, any kind of, you have some PDEs coming from physics, there are usually some units floating around. The way you describe the PD, I mean, the solution sort of depends on those, but if you relabel those, in a consistent way, you should still get a solution. So you have some symmetry on the solutions and relativity, it's like if you change how you're measuring space and time together. And then, it's natural to look at what's sort of a fixed point of that group action, and those are self-similar solutions. Okay, so why, and briefly, what's the point of self-similarity? I feel like I'm writing really big. Okay, so what's the point? There are many reasons. So why study this? Well, I won't talk about why study that because that's the universe. But why study this? There are a lot of reasons. I mean, so if you have if you have a sufficiently broad background in PDEs or physics, and then you'll just know in practice that these things are interesting. For us, I mean, one thing is that they are a source. They're often a source of interesting singular solutions. Source of interesting singular solutions. All right, and that's going to be sort of our main reason for looking at them. And in particular, they'll be related to something called naked singularities. So I quote something called naked singularities, which I'm going to do all of this in much more detail. This is just a quick overview. There's naked singularities, which is a type of solution to the Einstein vacuum equations, which has a singularity which is naked in some sense. I'll explain. And this is related to something called the weak cosmic censorship conjecture. Weak cosmic censorship. And so, by the way, for people on Zoom, is this text reasonable? Or
Perfect.
perfect. Okay. All right. I have no idea. It's hard to guess, but I mean, I can kind of see a small version of what you see. All right. Okay, anyway, that's like the 10-second overview. Now let me give well, no, it wasn't 10 seconds. That was my 5-minute overview. Now let me give a um slightly longer version of what the course is going to be. So my plan, so how's this? So, yeah. All right, so here's the rough plan. rough plan of the course, and part of it being rough is that I actually, it's presumably pretty unlikely that I'll actually get through all of it. But we'll see. Okay, so the first thing I want to do is kind of if you want a intro slash crash course to Lorentzian geometry. And GR meaning general relativity, right? Because I don't want to assume I mean, obviously it's useful if you've seen relativity before, but in principle, I don't, that's not necessary strictly. And so I'll do this sort of quick introduction to things. Obviously, lots of things will be brief, and if you want to understand things at a deeper level, you need to go, you know, read stuff. But and so in particular here, we'll discuss the initial value problem, which is fundamental to at least mathematical general relativity. I'll give have a discussion of Penrose diagrams. In particular, I'll give one precise definition of them, and we'll talk about the this thing I mentioned, the weak cosmic censorship conjecture. All right. Okay, so that's part one. So hopefully that doesn't take the whole course because then that would be silly. So I'll try not to spend too much time. But there's still a lot of stuff there. All right, that's kind of the intro thing. And then so we'll set the ground. We'll have, once we've discussed this and we'll have defined naked singularities, we'll have a sort of a key motivating thing. And then we're going to talk about self-similarity for the what is the spherically symmetric Einstein scalar field system. Einstein, um, yeah, Einstein real scalar field system. And also I'll talk about what that is specifically later. But basically, this is going to be the Einstein equations, which are coupled to an additional PD, a scalar field, but then we're going to study them under spherical symmetry. I'll discuss why that might sound weird, like why not do the Einstein equation spherical symmetry? We'll discuss that later. This turns out to be something simpler to look at, actually. So, and all the stuff, everything I'm going to discuss about this basically will be due to Christodoulou. And so what happened is that Christodoulou had a sequence of influential works in the 90s where he did many things, and most of those things we're not really going to talk about in the course. But particular thing he did was identify an interesting class of self-similar solutions to this spherically symmetric system, in particular ones that were interesting in relation to the notion of a naked singularity, right? And I'm going to go over those, right? And okay, that will be very the idea is later we're going to do things that are in principle more complicated, but this kind of having these in this setting, you can understand lots of things and you build lots of useful intuition for the later stuff. Right, so that's that. Then, right, then this board, yeah, so these two boards are good. Okay, so then, all right, so then we're gonna do that. Then we're gonna sort of change gears a lot, and we're going to move properly kind of to the Einstein vacuum equations. I'm going to discuss some sort of technical tools, some double null gauge, and the characteristic initial value problem. This is a certain way of looking at the Einstein equations that has been tremendously useful in the last, I don't know, 15, 20 years. We'll sort of go over that. Again, well, depending on interest, maybe we'll titrate the amount of detail. We'll see. All right, then, okay, so this we'll sort of suffer a little bit here to do some technical work, and then once we've suffered a bit, we'll maybe see some kind of cool, at least I think, cool connections to things. So then the fourth topic I'm going to talk about sort of Pfefferman-Graham what I'll call Pfefferman-Graham self-similar solutions. All right, so what are these are a class of self-similar solutions to the Einstein vacuum equations. Um, yeah, which Pfefferman and Graham were studying for reason they weren't actually their direct motivation was not um, sort of physical, but the this class of sort of a class of solution types that they found have are tremendously important, and so we'll discuss those, and then finally, um, the the last thing I want to do is discuss sort of something that more recent, something called what I'll call twisted self-similarity. All right, which is a kind of it's well, eventually you'll see you can sort of think of it as some kind of informal sense, a twisted version of these Pfefferman-Graham solutions. So it'll be some other kind of self-similarity, right, which is sort of twisted. And this type of self-similar solutions will show they can be used to construct um, naked singularities, right, for the Einstein vacuum equation. For the again, so 3 plus 1 relativity, we do this weird thing. We write, instead of writing 4, we say 3 plus 1. The 3 plus 1 dimensional, which is the 3 plus 1 dimensional Einstein vacuum equations. All right, so that's the basic plan of the course. All right, so in terms of prerequisites, um, I mean, like many things in math, if you're sort of sufficiently mathematically mature, principally you can learn what you need. But okay, but probably it's very useful to have be somewhat conversant with the main objects of Riemannian geometry. So I certainly won't assume Lorentzian geometry because it's not a particularly standard thing to have studied, and I don't want to have the course only be accessible to people who have already studied GR. Um, so part of this crash course I'll do here is just telling you how all the constructions, almost all the Riemannian geometry things have natural analogs in Lorentzian geometry, and then I'll discuss carefully what's different. Um, some, some PD background, particularly with wave equations, will also be useful, not necessary, strictly speaking. In general, and maturity with respect to analysis is useful. All right. So maybe any questions about the plan? And I think I can see the chat up in there. All right, cool. Then, yeah, let's get going. Oh, and also I will for on Mondays when there's the 2 hour lecture, we'll do a 10-minute break at some natural point in the middle of the lectures. Okay. All right, so let's start with this part 1. All right, like I said, hopefully this won't be the entire course. Um, okay, so what is Lorentzian manifold? Um, so what's a Lorentzian manifold? All right, well, it's a manifold. It's a manifold. And a manifold equipped with a symmetric 0, 2 tensor, which we'll call G alpha beta. So that's just like in Riemannian geometry, right? Except that um, it's not positive definite. It has this funny signature. So, which you can say in many different ways. Um, Maybe one of the more concrete ways is to say such that for every point P in the manifold, there exists the basis of of the tangent space at that point P, let's say, well, I guess let me say this is dimension, manifold of dimension one, dimension equal one plus n for some n bigger than or equal to one. So let's suppose we have a basis, the tangent space E0, E1, dot, 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 En. So at this point, we could pick a basis so that and so that G is equal to minus E0, E0, plus E1, E1, En. Right. Basically, you have kind of this one negative direction, and then the other directions are positive. All right. Okay, so like in Iranian geometry, you have an inner product on the tangent space. It's just that it's indefinite. All right, so now okay, there's of course the most basic example is Minkowski space. So this we'll refer to many times. So Minkowski space is the manifold is R4, and we usually refer to the Minkowski metric with an M, and it's just minus dt squared plus dx squared plus dy squared plus dz squared, where I'm writing this R4 is just t x y z, and labeling the four coordinates t x y z. Right. So the t, standing for thinking of this time negative direction. Okay. So let's. Ooh, sorry. Oh, actually, there's something I forgot to say. So, it would maybe be useful because I don't know people's backgrounds. If you are planning on, well, if you're here, I guess you're at least considering taking the course. So if you could send me an email, maybe just like say what your relevant background, sort of roughly what your background is and the things I said, because that will just be useful, like sort of PD or geometry background. Um, and then tell me if you've registered for the course or not. And that will be useful for me. Yeah. Okay, where are we? Yeah, okay, so we have this definition. Now we have another definition, which is important. All right, so if V is in, say, the tangent space of M at some point, and if V is not equal to 0, then we well, you could allow 0 or not 0. Anyway, there won't be the level of detail that we'll go right now, that won't be too important. But we'll say that V is time-like. Actually, let's allow 0. All right, so let's suppose you have V in the tangent space. We'll say it's time-like if when I plug it into my inner product, I get something negative. It's space-like if when I plug it into the inner product, I get something positive. And this is the weird one, it's null if when I plug it in, I get something 0. Right? Then these two things, oh no, these ones, but not this one. These ones, either of those is called causal. So I guess I did it in the wrong order. All right, so you would say a vector is causal if it's time-like or null. All right, and we'll see very quickly where this terminology is coming from. All right, so then again, just in the event that it's really your first time seeing this, just to orient yourself, right? So in Minkowski space, so Minkowski space. D by dt, right, is time-like, right? Just because norm is -1. Dx, dy, dz, for example, are space-like. Um, and for example, dt plus dx or plus or minus dx, for example, is right. So you should, if you've haven't seen these concepts before, make sure that's all clear. All right. Okay. So then, as usual, when you make a definition for vectors in a particular tangent space, you then there's the analogous thing for vector fields, right? So there's the all right. So if V is a vector field on M, then it is, whatever. It's either time-like, space-like, or null if, if V restricted to every point is whatever, right? So if it's time-like everywhere, okay. Um, Great. Then we have also important definition for, so this is for vectors, and then we have corresponding notions for submanifolds. So if, yeah. So if this and M is some submanifold, right? So then so we have an induced metric, right? So let H be the induced metric on sigma, right? Which is just obtained by restricting bigger metric. Right, then, right, we say this is space-like. It's space-like if H is Riemannian. Right, so if the induced metric is positive definite, then we say it's space-like. Um, blah blah blah. It's time-like. Blah blah blah. If you get something Lorentzian still. And there's this weird thing that can happen because, unlike the Riemannian case, well, basically because of these existence of null vectors, it's possible that you're neither Riemannian nor Lorentzian. You can just be something degenerate. You can have a direction that's always zero. That has a zero inner product with every other vector. So then we'll say it's null. Um, if H is degenerate. So if it's not an and by degenerate, I mean in the sense of an inner product, right? Inner product is non-degenerate if for every vector there exists some other vector whose inner product with it is non-zero. Okay. That's that. Questions? Right, just rolling through some definitions. Okay, then okay, well maybe let's just do the quick examples with Minkowski space. Right. Okay, so for example, the hypersurface T, so this is in Minkowski space. T equals 0 is space-like, right? So because you just the induced metric is just that you delete the dt squared, so then you got just normal Euclidean metric on R3. So say x equals 0 is time-like. So if you look at x equals 0, you just lose the dx squared in the induced metric to get minus dt squared, dy squared, dz squared. That's still Lorentzian. And then 3, for example, you can look at the hypersurface t equals x. This this one is null. Um, yeah, maybe that's worth. Um, well, yeah, I'll just say exercise. Make sure you understand that. All right. Okay, so that's that. Then there's an important, of course, well, all submanifolds are important, but the most common situation you deal with is hypersurfaces, which are codimension one submanifolds. And in that case, you can talk about you can use the notion of a normal vector, and you can relate these definitions to properties of a normal vector. So let's do that. All right, let's see. Okay, so here, all right, so if sigma and m is codimension one, meaning it's a hypersurface, then there will exist a normal vector, which I'll write as, let's say, n, okay, along. So that's a fact. What does that mean that it's a normal vector? This means that, so this means, so this means that for every v in the tangent space to sigma, for every v, well, how do I want to say it? So like, sorry. This means that if yeah, v is in the tangent space to sigma, if and only if g of the normal and v is 0. Okay, so that's a fact. All right, and there's a weird thing, unlike so in the Riemannian case, there's a natural choice. You could so you can always normal vectors cannot be unique because you can always multiply them by a constant, right? The inner product is linear. So if I multiply this by 2, it doesn't change that. But one natural way to pick the sort of a canonical choice is like the unit normal in Riemannian geometry. You pick one of length of 1. Then there's this weird thing in Lorentzian geometry that it could be the case that your normal vector is null. And then there's no, at this level of generality, there's no sort of canonical way to pick its size. And that's, kind of annoying, but a source of various things. All right, so you always have to keep in mind there's this an ambiguity in normals to, if you have a null hypersurface, then its normal vector will be null. Well, I'm going to say that right now. So in the event that your normal vector is null, two reasonable people might disagree on what the. All right, so let me write this out now. Okay, so here's some facts. Again, I'm not, you really should make sure if you haven't seen this stuff before, you should really make sure that you understand these things thoroughly. All right, so if your normal vector is time-like, that is the same thing as sigma being space-like. Two, if your normal vector is space-like, that's the same thing as sigma being time-like. Three, if your normal vector is null, that's the same thing as sigma being null. And again, let's just quickly look at those, go back in terms of those examples. So in Minkowski space, right? So for t equals 0, one choice of normal vector is d by dt. D by dt is time-like, so that is space-like. So for x equals 0, a normal vector could be d by dx. Right, and so this is space-like, so this was time-like, we said. And then we have the weird one. So if you're on t equals x, then your normal vector is dt plus dx, which is strange. So no, because dt plus dx will in fact be also tangent. Right, which is again, if it's your first time thinking about Lorentzian geometry, is sort of disturbing that things when you have a null hypersurface, the normal vector will be tangent. All right. So again, just for the sake of time, I'm trying moving through these things fast, but if you really should play around with these things if you haven't seen it before. Okay, so that's that. Questions? All good. All right, let's keep going. Okay, so just some more. These first lectures, there's a lot of definitions. All right, so now we have definition, a time orientation, on a Lorentzian manifold MG is just a continuous choice. Well, I could say it different ways. I'll say it like this, is an equivalence class of time-like vectors um, or actually, I prefer this other way of saying it. Is a choice of a nowhere vanishing of a nowhere vanishing time-like vector. All right. Again, so of course, at this level of generality, which of these definitions, which is not really this level of generality we'll see is not quite relevant, fully relevant. But anyway, this level of generality is certainly not the case that every Lorentzian manifold has a time-like vector field. There's some topology, whatever. If you're bored, you can think about it. It's not really relevant, or it won't be that relevant for this course though. All right, so then once you have this, so once you have, so let's call this guy T, let's call this call this vector field T. Then once you have T, you can say that so a time-like vector V is future pointing if its inner product with the T1 is negative and past pointing if its inner product here is positive. Um, okay. So just to make sense of this quickly, you want to just draw the relevant pictures in Minkowski space. So on Minkowski space, we have all right, so if here's some point P, there's this usual picture you've probably seen. All right, so you have these cones, these cones, um, and sort of everything up here is so here's like d by dt is pointing here, right? And then the spatial ones are that way, right? So there's time length. Everything down here is also time length, right? Because minus d by dt is also time length. You take minus d by dt with minus d by dt minus minus plus. Right? So everything out here is space like, and everything out here is space like, right? And then the boundaries are null. Okay. And so you can see what another way to think about this time orientation is it's just so at every point on a Lorentzian manifold, every point, the tangent space is of course a copy of Minkowski space. So you have this picture sitting infinitesimally. And this time orientation is basically saying that you can continuously pick on the whole manifold a choice of like one side of this cone to call the future one, right? And that's really some topological thing, right? Whether you can do that or not. Anyway, so we make that choice. Okay. So yeah, if you can't make the choice, we make that choice. Okay. Well, I guess here, um, yeah, I mean, I said this for time-like, but you can also use this definition for causal link. So what's next? Okay, so now with those, we can make some definitions. So let's do definition. So, well, actually, sorry, do it like this. Hey, so we say, so if gamma, say from some interval into our manifold, is and there are different conventions people use for this course, sort of the different classes of curves people use, and for some applications, it's very important to think about that. Um, for us, it won't really be. So let's just say if this is a piecewise smooth, piecewise smooth curve, then we say gamma is going to be time like if gamma prime. So we have this thing except at a few points if this is time like. This is time like, we're defined. Um, and causal if you just replace causal. Okay, so that's fine. And now we come to an important definition. Well, these are all important, but All right, so J plus of some point P is going to be, well, let's just throw in P. So we don't have to think about our conventions of whether the zero vector counts or not. As something causal. So P union, so we include our point, and then we say all other points in our manifold such that there exists gamma from say 0, 1 to M with, oh, and then there's also I forgot, you can also append future or past all these definitions, right? So if when this thing exists, if it's time like past, if time like and future oriented everywhere, then I would call this a future time like curve, et cetera. All right, so J plus is going to be all P, yeah, P and then all Q such that you can find a curve with such that gamma is say future causal and gamma connects the points. So gamma of 0 equals P, gamma of 1 equals, all right. So yeah. All right, and then okay, then there's the minus is all the same, but you say past instead of future. All right, so I'm assuming here that we fix the time orientation so that it makes sense to talk about future and past. All right, and then we have so we also have the variant where we switch causal instead of requiring the things to be causal, we make the things time-like. And that gives you another object. All right, so if you replace causal with time-like, then you get I plus or minus. All right. Okay, and then all right, so then once you've defined it also at a point, you define it in a region by taking the union of all the points. Let me not write that. Okay, so all right, so now let me just briefly say, so what's one of the important things about this is there's a direct sort of physical interpretation of these things. So in, let's say, so in at least classical general relativity, all observers, whatever that means, are required to travel along causal curves, along, let's say, along future causal curves, right? And moreover, if your observer is massive, if you can say observer, or if you want, you can say a test particle, something very small compared to, the space-time. So if your particle has mass, it's massive. This doesn't mean that it's very large, it's that it has mass. Um, then the curve should actually be time-like. And if it's massless, so this would be like a photon or something like that, then actually the tangent vector should be null everywhere. So we should have a null tangent vector. And so you see, so if you already, once you have fixed some Lorentzian manifold and have declared that it's space-time, just studying just already the geometry of these sets is already telling you something about the physics, telling you what's accessible to different points, at least by test particles or observers. Questions? All right, so maybe that's a good moment to take a 10-minute break. So let's reconvene at 4 05. All right, so it's 4:05. So let's get back at it. Where was I? I finished writing here, right? Yeah. Okay. So yes, we made this definition of the J, of P, and the I, and noted that those, so if you're determining those, it already gives you is telling you physical information about a space-time if you know that that space-time is physical. Um, again, let's quickly just see what these things mean in Minkowski space. Right. So if we have a point, well, I already drew up there. There's the light cone, right? I mean, so yeah. Oops. So if we have here, so here's some point P, then so here's sort of exercise, you know, check. So I plus of P is just the inside of the is the top. Well, I don't know. Yeah, inside of top of the light cone. You might say, well, first, I remember, I think when I first saw this, first you say, well, isn't that obvious? And then someone says, why is it obvious? And I go, oh, it's a little less obvious. Anyway, make sure you understand. Um, right, and then J plus is, so this is like strict inside. So not including the boundaries, because these points, well, certainly this naive curve, which connects points here is null. That doesn't work. But then, so that would be strict, and then this J plus would be that you know, include the boundary too. All right. So again, it's a good thing to make sure you understand. They're uh if you'd like further references for these kind of things, send me an email and I'll tell me your background and I'll send you and I'll then I can recommend some references. Okay. So that's that. Okay, so that's sort of basic definitions of causality. All right, now again, I'm going to do some more kind of just lightning, you know, trip through Lorentzian geometry, which mostly consists of saying that various constructions of Riemannian geometry that look like they should work do work, right? So anything where you didn't like divide by the norm of a vector is basically fine. All right, so let's just do that. All right, so basically, you know, so we have so covariant derivatives. Geodesics. Well, I'll say in a second, but more about that. But and curvature, you can roughly think are defined as in Riemannian geometry. Um, you know, as long as you don't invoke that something's positive, definitely. You know, so don't. Um, so I'll say in a second. So for example, you have the same formula for Christoffel symbols. You know, well, I don't even know if I really need to write this, but for some reason it's in my notes, so I'll write it. Um, yeah, just the usual thing. Right, you have those. So those formulas are all the same. And then uh for you know, this is the inverse metric, et cetera, et cetera. So I'm skipping lots of things, right? Okay, and then so you could think, so don't think about geodesics, at least at this first pass, as you know, minimizing distance. Don't think about a metric space structure right away, but you can what you can think of is just solutions to the same equation, right? Which is, of course, the Euler-Lagrange equation of suitable functional, but forget about that. All right, so solutions to that equation we'll call geodesics, right? So a solution x of tau to this is a geodesic. All right. All right. And as an aside, I had this little blurb up here about, this physical interpretation of a causal curve or time like or null relating to possible paths that um, test particles or observers can go on. So geodesics have a similar interpretation. So in geodesics are what? A test particle in quote free fall, again, whatever that means, moves on a geodesic. All right, so well, whatever it means. What it means is that it's not if it's not exerting any forces, or like you're not on a rocket ship, trying to modify your path. If you're just falling, then you will move on a geodesic. So therefore, solutions to the geodesic equation also have, in that sense, directly have physical relevance. Um, all right, that's that. Okay, so then curvature. They're all the various ways to think of curvature. Um, let's see, one of the more concrete ones is the lack of commutation of covariant derivatives. So I'll write it in this tensor form. So I'm taking two covariant derivatives. So if I say this is say a one form, I'm looking at the Hessian of the one form. So that's three indices. I can flip the direction of the derivatives. So of course on Minkowski space, the equality of mixed partials tells you this is zero, but in general, like this gives you the curvature tensor is exactly like in Riemannian geometry. Um, right. I'm assuming these things I have written in my notes are correct. Doesn't really matter for now. Okay, so anyway, curvature is, lack of commutation of covariant derivatives. Of course, when covariant derivatives hit a scalar, they always commute, right? All right, and then so this is the full curvature tensor. This is a 0, 4 tensor. It has all those symmetries, has the same symmetries as in Riemannian geometry. It has these symmetries as in Riemannian geometry. It has this because it's the same definition, really. So the same algebraic reasons work, right? Right, and then you can form, so this important object for the actual Einstein equations is the Ricci curvature. That's going to be the trace of suitable trace of the curvature tensor, right? The Ricci curvature, and then you can trace the Ricci curvature and get the scalar curvature. Right, those are the same definitions as in um, Riemannian geometry. All right, and so now we can state the Einstein equations somewhere. All right, so feels like they deserve a new board. There. Well, let's go here. All right. So I stated the Einstein vacuum equations with zero cosmological constant at the beginning, but and that's what we're going to study. But just for sort of completeness, let me say, so in general, so Einstein equation, sort of a general form would be, so that be, so again, so you start with the Lorentzian manifold, and then we're going to ask that Ricci curvature minus 1/2 of G mu nu times the scalar curvature plus some constant. So this is the so-called cosmological constant. All right, times G mu nu, that this equals, then you can put constant, some 8 pi sometimes, but not that important. Times something T mu nu, where T mu nu is T mu nu is some 0, 2 tensor which is determined by your matter. If you have matter content is determined. So this would be the energy momentum tensor of matter content. All right, so if you're doing classical astrophysics, the first thing you'd probably want to put there is like a fluid describing a star, but there are many things that you do. So when we talk about Christodoulou's work in the spherically symmetric Einstein scalar field system, this will be the energy momentum tensor of a scalar field, right? Um, okay, anyway, that's the general one, and it's a little linear algebra exercise, right? That if this equals zero, if the cosmological constant and this t equals zero, then this becomes the equations are the same as Ricci of G. So that's essentially linear algebra effect. Right? Questions? Nope. Cool. All right, so let's keep going. Oh. Oh yeah, there was a question and during the break about how um, one will be evaluated if you're taking this for credit. And so there will not be homeworks or anything like that. But if you are taking the class for credit, then and we'll think about due dates later. But basically, what I'll want you to do is find some application of self-similarity, and kind of self-similarity shows up almost everywhere, almost all parts of mathematics in some way or another. So no matter what your actual research interests are, you should be able to find something. Just find some paper, like a research paper that uses self-similarity, and write me, some kind of summary of it, at least say 5 pages or whatever. Just so that you try to engage with some of the ideas from the course, maybe in a way that's more directly connected to whatever you're doing. Of course, if you're into relativity, you can write about something in relativity, but that's, you're not restricted to that. All right. Um, okay, back to this. All right, so that's all of that. Okay, some other definitions. Yes. Okay, so all right, let's now move on to um all right, so now I'm going to soon introduce the notion of global hyperbolicity, um, which is a very, very deep notion that I'm going to go over very fast. um, but okay. All right. So first, let's talk about an extendability. Right. So a curve gamma um, from I to M is inextendable. Well, I mean, if you can't extend it, if there does not exist um, an immersed curve, say J tilde, from some interval J to M with such that this J, such that with J strictly including I. All right. So in particular, for J to strictly include I would have to be a finite, right? So I guess I didn't write, right? And these are all in R. So J strictly including I, and such that on the in gamma tilde restricted to I is equal to gamma. All right. That's just exactly what you would think the definition is. Can you make the curve bigger? Right, and then okay, and then this leads to one important definition, right? So we say G um is geodesically complete if all inextendable geodesics, if all inextendable Geodesics, remember, geodesics are defined to be solutions to the second order ODE, not second order ODE. All inextendable geodesics gamma from I to M have I equal, you know, they exist sort of their domain is as big as it could be. All right, then you can add in all the adjectives you want. So if you want to, you can talk about time-like geodesic incompleteness, causal geodesic incompleteness, etc., just by appending the adjective to the corresponding um in the definition. All right. All right. Okay, so now very important definition. Um, all right, so we'll say that, so let's say a hypersurface, let's even say a closed hypersurface, sigma in M is a Cauchy hypersurface. Let's even say closed. Let's make it space-like. Why not? All right, so closed space-like is a Cauchy hypersurface if every my hands I didn't gotten rusty over the break. If every inextendable causal curve in M intersects sigma exactly once. All right. Okay, so if and all right, so related to this, so if MG has a Cauchy hypersurface, has a Cauchy hypersurface, then we say M is globally hyperbolic. Okay. All right, so this is a pretty deep definition, and but even if it's your first time seeing it, what is hopefully and can be intuitively clear is that what this sort of tells you. So remember, something causal, if you know, is what, say, a test particle or an observer has to travel on. So, you know, and remember that M represents space and time, and the Cauchy hypersurface is something that, you know, you hit, you know, exactly once. So it's kind of, which means that sigma is a reasonable notion, is like reasonable as an instant of time, you know. Okay. So that's fine. Um, so that's sort of clear. What's unclear is why this is still a particularly useful way to capture that. And well, what's even more subtle is that these turn out to be the exactly correct class of spacetimes to study hyperbolic PDE on, which is um, not an obvious thing at all. Okay, but let me give, as usual, the Minkowski example. So Minkowski space, right? T equals 0 is a Cauchy hypersurface. Right. So again, that might, you might think, oh yeah, that seems plausible, but then, make sure you actually know how to do it. It's actually not, again, if it's your first time with the concept, this might seem more straightforward than it is. And again, if you want more references for these things, please email me and I'll be happy to recommend things. All right. Any questions? Yeah, so exercise. Exercise. Do this exercise. Really make sure you do it. All right. Yeah. Okay. So then what do I want to say? Oh, actually, something back about these. Again, if it's so I gave this general form of the Einstein equations, but I sort of didn't. Maybe I should just give a little more context about what, you know. Well, I said something about the T, that's the matter content. Um, maybe let me quickly say something about the lambda. All right. So 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 I'm sort of skipping back over to that part. So how should you think about the cosmological constant? All right. Well, basically, I mean, so as a mathematician, essentially all any value of the cosmological constant is pretty interesting, and there are lots of hard questions to ask, and things are known, things are unknown. So in that sense, you could just be open-minded. But it's also useful to think physically what's going on with them. So in this course, we're going to focus on lambda equals 0. Of course, that's the one which kind of makes the equations look simplest. But physically with this is relevant when you want to model isolated systems. So isolated is what usually is, I mean, usually is used to model sort of isolated system. What does that mean? That's like a, you know, like a single black hole, not close to anything else, or maybe two black holes um, merging or something like that. Right, this is usually what's used there. Positive cosmological constant um, is generally used when you want to model it is the current understanding of things is that is the useful way to model the entire universe. Again, I say model because I mean, they're also there. You can capture some of the phenomenology here by adding suitable matter here. It's a lot of these things are choices. Um, but okay, so there's that, and then finally there's lambda negative, which doesn't really have an application in classical astrophysics or classical relativity, but is something of great interest in I'll just say in high energy physics. Um, Various quantum things, people are very interested in that. So any of these things have lots of sort of physical stories behind them that can be used to come up with interesting mathematical problems. All right, so that's a natural place to ask for question before we talk about the initial value problem. All right. Okay. All right. So now the next topic is the initial value problem. Yeah. All right. So this is so sometimes called the Cauchy problem or the initial value problem. All right. So what maybe just say a few words. So general relativity is a part of at least the this classical relativity is embedded in the name is a part of classical physics. And the usual way that we understand questions in classical physics is through there's some underlying initial value problem. So you have some like like a Newtonian mechanics, the position and velocity, and then something happens, right? This is the framework, sort of all, at least one way to organize, and the standard way to organize questions in mathematical general relativity is to understand them as questions about the initial value problem. So there'll be some notion of data, which then you get a solution, and you say, under some assumption about the data, what do I know about the solution? So it's very important. This is sort of the theorem which allows the subject to exist, is that there is some reasonable way to have an initial value problem. Okay, so well, certainly at the level of discussion I've done so far, it's completely unclear why there should be such a thing or what form it should be. I mean, no, PDE doesn't really seem to have entered at all. Yeah, right. Okay, so let's get into that. Okay, so first there's we'll sort of discuss the first complication. I mean, you might think, okay, so what if there's going to be, if you have some naive, take of determinism, you would say, well, we have this notion of like a instant of time, this definition. So you think, okay, it's a space like, you have a hypersurface. It's going to be an instant of time. So I guess it should be like three-dimensional, Riemannian. Uh, if I fix that, maybe I can solve for something. That's, something like this. Maybe I need some more. Maybe I need the derivative of that too, or something like that, because maybe it's curvature is two derivatives, second order. All right. So already that's a little complicated because of so-called constraint equations. It's not that simple. So let me explain that. All right. So let's suppose sigma is a space is a it's a closed space like hypersurface. In our manifold. Great. Let's also and let's assume, yeah, and assume now that we solve the Einstein vacuum equation. So assume that for each E of G equals 0, right? Okay, so then we have there's some objects. So once you have the space like hypersurface, there's some natural objects that are induced from the bigger manifold. So we have you have an induced metric, like my notes, I call G bar on sigma. All right, so because sigma is space like, this induced metric is Riemannian, right? So it's induced Riemannian metric on sigma. And then you also have the second fundamental form, the which is defined just like in Riemannian geometry. Right, so this is right, so I can say it takes the domain is the it takes two vectors, two tangent or two vector fields or vectors, goes back to R, and it's just defined by K of U V equals, well, they're different the subject where there are endless sign mistakes. Usually they don't matter, but sometimes they're important to not make it to not make. All right. So all right, so what do you do? So we have well uh yeah, there are different ways you can say it. So this is, so if I have two vectors u and v, I can take the covariant derivative of v, and then I can take the inner product with n, where n is the normal to sigma, which will be well, in this case, I can say is unit normal. I can normalize it. All right, so this is the same definition as in Riemannian geometry. And we know that in Riemannian geometry, the first and second fundamental form sort of give you, well, this is the first fundamental form that tells you about the intrinsic geometry. Then the second fundamental form tells you how the manifold sits in the ambient spacetime. Right. But they're one of these you may or may not remember from Riemannian geometry that there are equations which relate. So if there's some, you have the curvature tensor of the background spacetime, then you have a submanifold. So you should, in principle, I mean, everything on the submanifold is computable from the ambient spacetime, right? So therefore, you know, various things, curvature, for example, of the induced metric has to be computable from the curvature of this. Of course, you know, when we have this equation, Ricci of g equals 0, so you might wonder, so does this imply something about, g bar that will tell us, are there some constraints on what the geometry of a space like hypersurface could even be before we even really solve any PD? And there are, and I'm just going to tell you what they are. So it's a consequence. So consequence of the so-called of the Gauss and Kodazzi equations. So you have to take some traces of them. Of the usual ones are the following. So you get, all right, well, you have, so I'll use my barred quantities refer to the induced metric G bar. So it turns out that the scalar curvature of G bar plus so you take the trace of K. So K is a tensor. It's defined on along sigma. So this trace is with respect to G bar. So the trace of the second fundamental form squared, then minus there's this, write it like this, of this sort of contraction of this thing with itself. This has to equal 0. And all right, and then you also have something just of the second fundamental form. So this is, I'm using the bar here. So this is the induced covariant derivative on the hypersurface. That this will basically have some kind of divergent, well, so I'm going back and forth between also index notation, covariant, hopefully that's not too confusing. So this is the divergence of K minus the covariant derivative of the trace of K distance. So, all right. I've also, implicitly here, we're raising and lowering indices. That's just like in Riemannian geometry. Okay. Okay, so you have these. So these equations are, so if you have a space-time where Ricci of g equals 0, and you pick any space-like hypersurface there, then these things have to be true. All right, so ergo, if we're going to come up with a initial value, some version of an initial value problem, we can't just say I take an arbitrary Riemannian manifold and try to solve for a space-time to stick it in because, well, I mean, there are some equations, which, I can't just take an arbitrary Riemannian manifold and an arbitrary sort of second fundamental form and try to solve because, well, they better satisfy this. Okay, so these are called the constraint equations. Right, and so the focus of this course is not, we're not really going to talk about these, but it's worth remarking that, I mean, it's not so simple to understand what the space of solutions to this is, or though there's quite a bit known. I mean, even in the case, so there's the first as a warm-up case, you consider setting just K to be 0, right? Then you see that you're studying manifolds that have scalar curvature 0, which is kind of a whole, that's a whole thing that people do in geometry. There's not some simple characterization of there. There are things you can prove, et cetera, et cetera. So it's not simple to understand the space of them, but just from counting degrees of freedom, I mean, these are certainly underdetermined. So you should think there are a lot of solutions to these. They have some. They're not quite arbitrary, but there are a lot of them. Okay. But anyway, depending on, sometimes there are things you want to study where it's it can be quite annoying. You set up some problem and you think you can construct something, but finding the data which starts it to solve this is complicated. So anyway, they're kind of sometimes you can ignore them, but then sometimes they show up and they're very important. Okay, so um, yeah, so this leads to a definition. So let's follow in. All right, so let's let sigma, yeah, just say like sigma g bar be um be a Riemannian manifold, and um k be a 0, 2 tensor on sigma, symmetric, be a symmetric 0, 2 tensor are on sigma. All right. We say this is an initial data set. We say this is an initial data set if the constraint equations are satisfied. So if the okay, note maybe I should have, I think I didn't mention this, should have emphasized. I mean, note these constraint equations, right, are intrinsic. So I mean, they only involve, so if you K is a thing just defined on the tensor on sigma, right? And G bar is the metric on sigma. So these are equations which you once you have the G bar and K, you can forget about the ambient space-time, right? To ask if these are satisfied. So that's why this kind of definition makes sense, right? And note also, again, I'm assuming you're familiar with second fundamental form, but one of the you can think in sort of suitable coordinates, the second fundamental form is a derivative. What the second fundamental form tells you, you have a hypersurface sitting in an ambient manifold, that the second fundamental form is like the Lie derivative in the normal direction of the metric. So it's kind of like so if we have a space-like submanifold, then there's the time direction. It's kind of giving you like the first time derivative of the metric. Right? So you remember you can think of K as giving first time derivative of. Now it's a little that requires you to pick some coordinates, but that's in terms of its role as initial data. Again, curvature is a second order equation, so you might think two initial conditions, and so this is kind of like you have your initial metric, and then you kind of have the first derivative. Okay, 444. Okay, let's go over here then. Okay, so now we're going to introduce a definition which sort of says what does it mean to get a sort of solution corresponding to this. So we'll call this, at first we'll call this a development. All right, so let's let sigma G bar K be an initial data set. Okay, when we say mg is a development of this, if mg is globally hyperbolic, um, solves the Einstein equations, Ricci of g equals 0, and sigma embeds into M as a sigma embeds into M as a Cauchy hypersurface with induced metric G bar and second fundamental form. Right? Again, so it's sort of what you would think. So it's just saying you have, right, so you start with some Riemannian manifold sigma, just have the, so you're just given it intrinsically, and then this K, this tensor, there's this K here living in the tangent space of sigma. And then a development is if you can find some, some mg, which solves the Einstein equations, and where this really sits in mg as a Cauchy hypersurface. Remember, Cauchy, they were thinking that's like sort of saying that sigma is a reasonable as an instant of time. It's reasonable to think of it as like a time equals 0 slice, and you solve everything. All right, and so now what we want from initial value problem is one, well, do we always have a development? We'd like to always have a development, and then we'd like to understand what's very important is to understand to what extent is the object unique, right? Um, and of course, there's a silly, maybe I should say, there's a silly non-uniqueness. Like in ODEs, you have a second order ODE, you pose the two initial conditions, the value of the solution of a derivative, you get a local solution, and then you get uniqueness by saying you take the max solution, right? So we'd like similar thing here. Can we get like somehow they're the largest possible one? You can imagine that it's a lot more complicated here than in the ODE setting because there's sort of, well, again, I haven't even told you what's the PDE, where's the PDE hiding? But even forgetting that, I mean, it's just that the very background is not set. And so that conceptually is a bit confusing. Like, I mean, maximal, how, like, you could just have, if you have two solutions, how do you compare them, right? Et cetera, et cetera. Nevertheless, those things can be addressed very successfully. I'll tell you the probably close by discussing those key theorems. All right, so here's a theorem. This is extremely important result due to Shlapentokh-Rothman. This is one person. Right, from 1952, which just says, okay, so let's I didn't talk about regularity for any of these things. So for now, let's just assume that things are smooth. Later, when we actually, do real PDEs, we'll have to say things like Sobolev spaces and stuff. But for now, let's not worry about that. Um, so let's say you know, every smooth initial data set has a smooth development. Um, that's good. Right, so that's the sort of like yeah, some kind of existence. But again, this is not, there's no uniqueness here. There's no how many, right? Right. So there's the same in the same paper. There's a type of uniqueness, which is also proven. The different ways to refer to it, sometimes called referred to as like local uniqueness. So let me write what it is and I'll draw the picture. All right. So if um mg and m tilde g tilde are two developments of the same initial data set of sigma g bar k. Um, yeah. Then there exists another development. Let's call this m check g check and embeddings j from m check to m and j tilde from m check to m tilde, um, which commute with the initial data embeddings. And, which sounds a bit confusing, but it is, you just draw the picture, it should be clear. Let's go here. All right, so the idea is, you have, so here's your sigma, here's one m, and then you say, well, there's also this sigma over here, and here's your tilde. But it's saying that in reality, there's some check, well, some other, right, there's this third one, but this third one has, it can be sort of, you can embed it into here, and you can embed it into here. So there's some, so it's like sort of a subset. Here's the check. I'm identifying the object with its image under the embedding. And, you know, and the way sigma sits in here, so with this last vague statement, which commutes with the initial data embeddings, because we have, in principle, the initial data this is just an intrinsic, this is a three manifold, or well, it doesn't have to be three manifold, Riemannian manifold with a symmetric two tensor sitting over here abstractly. The development all include specific embeddings of that. And then the embedding here, and it's just saying this, if you embed here and then go here, it's the same object as embed here and look where it sits there, right? And that means that it's reasonable to consider, um, you know, you can restrict both of these things, have a kind of, and you can consider them to have a non-empty intersection, and that you can shrink them down to something smaller, and you get two Lorentzian manifolds which are isometric. Right? So that's the local uniqueness. So you can think, so it's kind of like saying after shrinking, you know, solutions agree. Right. So this is kind of, again, if you think about the ODE case, this is what's true if you have two. Um, so again, I said you don't have uniqueness of any solution to the standard ODE setting because you can just stop your solution at any moment. But you always have this kind of uniqueness that if you shrink the sort of domain of one of the solutions, then they eventually agree, right? But of course, I mean, this was a very extremely important result, but it's not, but I mean, if you want to do physics in a setting where you want to have determinism, you need to be able to talk about the solution. So you still, it's great that you could shrink these and get something common, but like, what about the stuff before you shrink? It's not fully satisfactory. And in um, the last 3 minutes, I'll just say the final result, and then we'll talk about it more on Wednesday. And I'll also talk about a bit how these are proven. All right, uh, so it's another theorem. So this one took. So again, there's Choquet, but then there's also Garish, and this was quite a bit later, 1969. Well, not quite a bit, but later. And what they proved here is that there exists a unique maximal. This is the key maximal development. All right, so meaning call that MG. All right, and this is really what you want. So this says so i.e. so if M tilde G tilde is another development, um, then there exists an embedding of J from M tilde G to MG, which again commutes with the embedding of the data, commutes with embedding of data. So this is this theorem, which really allows you to ask, all the questions basically that you want to ask. I'll get to like the cosmic censorship conjecture. All these things are going to be, so therefore we can make some assumption about the data, and then we want to prove something about the maximal development of the data. Right? This is the theorem which allows the modern mathematical sort of version of the subject to exist. All right, so that's 5. So I guess we'll end there and see you on Wednesday.